Next up is question 7. It says, determine if the lines are parallel, skew, or intersecting. If they intersect, find the point of intersection. Okay, so before we jump into part A, let's look a little more generally at, say, two lines, L1 and L2, and let's say they are parallel. Okay, so if you have two parallel lines in R3, what does that say about their direction vectors? Well, that'll say that the direction vectors are themselves parallel. So in other words, one is a scalar multiple of the other. Okay, and this is analogous to what you know about two parallel lines in R2, right? Two parallel lines in R2 have the same slope. Okay, so here we're saying that in R3 the lines are parallel provided their direction vectors are parallel vectors. Okay, cool. So what about two lines that intersect in R3? Well, that just means, right, there's a point in common to both lines. Okay, so now in R2, really this is the full picture, right? Either, if you have two distinct lines, either they are parallel or they intersect in one point. Okay, now in R3, there is a third scenario. And this is where the two lines are not parallel and they're non-intersecting. Okay, so I've drawn these two lines here, and this little break is just indicating that L2 is set back. Okay, so they're not parallel and, well, they don't intersect. So in this case, we refer to the lines as skew lines. Okay, so again, going back now to question 7, part A, we're given this pair of lines, and they're described in parametric form. And our job is to determine whether they're parallel, skew, or intersecting. Okay, so let's check whether the lines are parallel. Okay, well, from what we saw in the last video, right, we can extract a direction vector from parametric equation for a line by looking at the coefficients of the parameter. Okay, now one quick note here. You may very well wonder why I'm using t for the parameter for L1 and s for the parameter for L2. Well, that's just to distinguish the two parameters and to really emphasize that one doesn't necessarily depend on the other. So if I'm thinking about, say, t as time for parameter L1, I could just as well think about s as denoting time for L2, but I don't have to be quote-unquote on the same stopwatch for L2 that I do on L1, right? So this time parameter, in other words, can be completely independent of the time parameter used for L1. Okay, so that's why I'm using the different letters. So yeah, anyways, going back, right, we can see that the vector 2, 3, negative 1 is a direction vector for L1, and 1, 1, 3 is a direction vector for L2, and these are not parallel vectors, right? Why? Well, if I try to scale, say, the vector v2 to get the vector v1, I run into a problem, right? To scale the I component appropriately, I'd have to multiply v2 by 2. But then that breaks down for the j and the k components, right? Because if I multiply the 1 here for the j component of v2 by 2, I don't get 3. Okay, so these are non-parallel vectors, and so L1 and L2 are not parallel lines. All right, so then we can check whether or not the lines intersect. Well, if they intersect, okay, there must be values of our parameters t and s, right, that give us equality for the x coordinates, the y coordinates, and the z coordinates. So in other words, we're looking for values of the parameters t and s that make all three of these equations true. Okay, so let's just look at the first two equations, right, the x and the y equations. And from the x equation, note that if I add 1 to both sides, I get that s is 2 plus 2t. And then in the equation for y, I'm just going to replace s with 2 plus 2t, and that gives us 3t is equal to 4 plus s, which is 2 plus 2t. Right, now solve this equation for t, you get that t is 6. And then since t is 6, s would be 2 plus 2 times 6, so that's 14. Okay, so t equals 6 and s equals 14, right, satisfy both the x and the y equations. So if there is a point of intersection, it'll have to occur for these values of the parameters, but we have to check all three coordinates. So here, right, we need to check the z coordinate. So plug 6 in for t and 14 in for s, and you'll notice, right, we do not have equality of z coordinates for L1 and L2 for these values of the parameter, and so our conclusion is that these lines do not intersect. So the lines are not parallel, and they don't intersect, so they're skew. Okay, cool. So now let's go ahead and check out part B. It's the same question, just different lines. So here the lines are presented as vector functions. Okay, so we have 1, 3, 2 plus t times the vector 2, 2, negative 1 for a of t. That's L1, and then b of s for L2. That's 2, 6, negative 2 plus s times the vector 1, negative 1, 3. Okay, so I'll go ahead and just note here, right, you can also just write them in condensed form by just combining these two vectors, right, and then you're just reading off component functions there and there. So just like we did in part A, let's check if these lines are parallel. Okay, so a direction vector for L1, well, you can just read the coefficients off of t, and notice when written in this original form, right, this vector that's being multiplied by t really is a direction vector for L1. This actually is the form of what I called the vector equation for a vector equation for L1, and it's of the form R0 plus t times a direction vector v, right? And so that's really what we're looking at there. So 2, 2, negative 1, that's a direction vector for L1, and then for L2, right, that's we can use the vector 1, negative 1, 3. That's the coefficients there of the parameter s, right, as the components. Cool. Are these vectors parallel? No, they're not parallel again, right? If they were parallel, I could multiply, say, v2 by some scalar to get v1, but again, that scalar would have to be 2, right, to get the I components to line up, but then it breaks down for the j and the k components. So we conclude that the lines are not parallel. Are they intersecting? Well, just as we did in part A, from the first two equations, I see that s is negative 1 plus 2t. Now plug that in for s in the equation for y. So you get 3 plus 2t is 6 minus the quantity negative 1 plus 2t. And you solve for t, you get 1, and if t is 1, plugging that in up here, you get that s is negative 1 plus 2 times 1, and that's also 1. Check the z coordinates. So plug 1 in for t and 1 in for s, and here you do get equality. So in this case, we conclude that the lines do intersect, and they're going to intersect at the point when both t and s are equal to 1. And so to find those coordinates, just plug 1 in for t. Okay, so for a of t, well, if you set t to 1, you're going to get 3, 5, 1. And notice you also get the same thing for b of 1, right? 3, 5, 1. So that is our point of intersection, and that is going to do it for this video. Thanks so much.